and welcome back for another round. This is Mr. Doolin. I thank you so much for tuning in. Today what we're going to do is we're going to take a look at solubility equilibrium, and specifically for solubility equilibrium, we're going to look at the common ion effect and selective precipitation. So we're going to start with the common ion effect. And so what the common ion effect actually, or what a common ion is it's an ion that is already in solution that is identical to an ion produced from the dissociation of our solid. All right, so let me say that again. So it's an ion that is already in solution that is identical to the ion produced from the dissociation of our solid. Okay, and so you want to make sure that you actually get that definition down. So if you didn't, please review and rewind. And so the example that we're going to look at is silver 1 chloride, or just silver chloride. And the dissociation reaction is Ag plus and Cl minus. And so if we had a common ion, that means we're either going to have a silver ion in solution or we're going to have a chloride ion already in solution. So let's take a look and see what a common ion effect actually is. So if I dissolve AgCl, let's say in 1 molar NaCl. Well, remember, this is a group 1 salt, so it's completely soluble. We're going to assume 100% dissociation, very large K value, all right? And so what's going to happen in this particular case, right? If we tried to dissolve silver chloride in 1 molar solution, what would the effect on molar solubility be? Well, if we just justify this based on Le Chatelier's principle and we say, oh, I got products over reactants. If I'm going to increase products, my reaction will shift back towards decreasing the products and producing reactants. So I would expect it to actually decrease the amount of silver chloride that is soluble. If you didn't get that, go ahead and pause that and reason that in your head, because that's one of the logical arguments with your Q values that you should actually be able to make at this point. All right? Okay, so let's actually look and see what it does mathematically. So let's go ahead and set up a quack table. So I got Q, C, and K. Right? Now remember, I'm getting rid of the solid. I'm not gonna do anything with that. Now here's where it becomes interesting, because generally, if I'm gonna drop a solid into solution, my initial values, my Q values here, are going to be 0. All right? But in this particular case, since I've got 1 molar NaCl, really what that means is I've got 1 molar Na plus and 1 molar Cl minus by the time those dissociate. So this actually now has an initial concentration or Q value of 1 molar. All right? And it's still going to be X and X in my quack table because I'm still heading towards products, because that's where I've got that 0, right? And so now I've got X and then 1 plus X, right? And so setting up the Ksp equilibrium expression, I've got, it's going to be X and then 1 plus X. But remember, I'm going to ignore that, where it's going to be the 5% change rule, because remember, I guess from a previous lecture, let me go ahead and give you the Ksp value. So for Ksp on this, Ksp is equal to, let's see, what was it? 1.8 E negative 10. So I have a very small Ksp value, which tells me I don't go very far in the forward direction, right? Reactants are generally favored here, so I don't get much dissociation. So I know this change here is actually going to be insignificant. It falls under that 5% rule. So really what happens is Ksp equals 1x, because it's 1 times x, right? And so what it does is it significantly decreases this molar solubility if you solve this out. So without 1 molar NaCl, remember our X value equaled 1.34 E negative 5. And all I did, since this is a 1-to-1 ratio, if you look at it, Ksp is equal to X squared generally, right? Because it's a 1-to-1 ratio. So that's where I got this X value from, is I just took the square root of the Ksp value and got me X without the NaCl. Now with NaCl, my X value is equal to 1.8 E negative 10. So notice having that common ion significantly decreased the molar solubility of my silver chloride. And again, that is an expected result based on if we go back to this products over reactants ratio, because in this particular case, right, my Q value would actually be greater than K if I had all of that in there, right? And then it would cause the reaction to form more solid, right? And so again, these arguments of the products of a reactants ratio that exist at equilibrium is a very important. You've seen that pop up over and over and over again. So please make sure that you understand conceptually, right, that if we change that ratio from a reaction at equilibrium, that it's got to readjust itself so that it gets back to that particular ratio. Now, this technically, if you really want to think about it, it's not an equilibrium. I guess not a Q versus K, because we're not technically at equilibrium. We're just predicting which direction the reaction is going to go based on a Q value, okay? All right, and so this is generally what's going to happen. Just pay attention to the common ion effect. Look and write your dissociation reactions out and check to see, hey, if I'm dissolving this in some kind of solution already, are one of the ions common to what's going to be produced in dissociation? And then the trick becomes that the molarity of that particular ion that already exists becomes your initial value, and then most of the time you're able to use that 5% rule to ignore that X in the quack table. All right, and so now what we're going to do is we're going to take a look at selective precipitation. So I'm just going to put a couple of different ions. I'm only going to draw 3 of them in here. And then we'll put 2 different ones. Let's say we'll do silver and lead 2+. Let's do lead 2+. So Pb 2+. And the reason that I'm doing that, and you would ask, hey, if these are going to be insoluble, Mr. Doolin, how do I end up with ions in solution? Well, if I dissolved AgNO3 and Pb lead 2 nitrate, if I dissolve those in solutions, I know they're soluble because they have those nitrates, right? And remember, those nitrates are always soluble. And so what would happen if I take this solution, right, and I actually titrate with, let's just say, NaCl. Let's stick with that. Now, the thing that I know is that AgCl, what we just saw, it has a Ksp equal to 1.8 E negative 10. What you might not know is that lead 2 chloride also has a Ksp value, and that's equal to 1.6 E negative 5. And the question probably popped up in your head right now, hey, am I going to have to know all these Ksp values? And the answer, of course, is no, right? This isn't about memorization. This is about conceptually understanding the chemistry here, all right? So what I would say, and what you would be asked here, is if I wanted to isolate and purify one of these ions or purify these metals away from each other, which one would selectively precipitate out of this solution first? Because if I can identify it and get it to precipitate out as a solid, then I've separated my 2 metal ions. And this is a very common procedure that we use to purify metals, because most of the metals that come out of the ground exist as some kind of ore, right? It's a mixture of a lot of different metals, and so we can use the Ksp values of these particular metals, all right, based on binding with another ion, and actually precipitate and purify these metals away from each other. So this is a very, very common practice, to be honest with you. All right? Okay, and so let's go on. I'm looking at this, and the question becomes, if I'm going to titrate that solution with the silver and lead 2 ions in it, which one is going to precipitate out first? Well, if I'm looking at my Ksp values, we can kind of take a look and take a guess and say, well, the one with the lowest Ksp value is going to be the one that is the most soluble, right? Because it should have the highest molar solubility. I should be able to dissolve more moles per liter. Now, this is kind of tricky because remember I told you to be careful and watch out for this, because this is a 1-to-1 ratio and this is a 1-to-2 ratio for my dissociated ions. So what happens is my Ksp for this equals x squared. My Ksp expression for this ends up being 4x cubed. So you always want to double check when you have those different ratios and just make sure that the solubility, the molar solubility, works out. Because to be honest with you, solubility is really based on that molar solubility. I can look at the Ksp values and make predictions, right? But if I have different ratios like this, I want to make sure that I actually go through and determine that X value. Now, if they were both 1-to-1, we can look at Ksp values and rank solubility all day long, right? Because the X values, you end up taking the square root, say, for example, a 1-to-1, and it all mathematically is proportional. So the X value for this one is equal to 1.34 E negative 5. The molar solubility for lead 2 chloride is equal to 1.59 E negative 2. And so what we see is lead 2 chloride has a higher molar solubility. And so what that does tell us is that I can get more moles per liter. So remember, as soon as my X values go above that point for silver chloride, I'm going to get a precipitation, because then again we're back to this Q versus K, right? For this, when my X values climb larger than my molar solubility, I've got a supersaturated solution, and that's when I get precipitation. And so the question that pops up a lot of times too is they'll say, hey, after we titrate all of the silver chloride out, or all the silver ions out, what's the concentration of the silver ions in solution? Well, it goes back to conceptually understanding, do you understand what insoluble means, right? And so if we precipitate all of the silver chloride out, right, represented by the green down there, what that means is I'm going to think of it as I'm going to precipitate all of those silver ions. They're going to be solid. Well, what do we know about silver chloride as a solid? Well, it dissociates back into its ions, and then I can use, right, my Ksp expression, my molar solubility, and determine exactly, hey, if I just dropped solid silver into this, what would be the concentration of the ions in solutions? And so we actually solve for that already, right? And so the trick for these kinds of problems, ladies and gentlemen, because they will ask you sometimes, hey, if I've got this mixture of metal ions, I'm going to precipitate, which one will precipitate first, right? And that's the one that has the lowest molar solubility will precipitate first, and then they follow that up with saying, what is the concentration after all the precipitation has occurred, right? And then we have to go back and treat it just like a solubility equilibrium problem, because we will have that solid in solution, and we understand that some of it is going to dissociate even though it's a very small amount, okay? All right, ladies and gentlemen, that was a lot of information. Hopefully you're good with the Q versus K. If you were good with Q versus K before coming in, you probably didn't have a whole lot of questions. But if you did, get them down. I'll see you in tutorials for those. And otherwise, I will see you in class.